Alrighty. First things first. I don't know what happened when I wrote this, but there was a bunch of things and nobody told me. So I also blame you guys. Um, spring break I had backwards with the midterm. I thought spring break was the last week of February. It's the first week of March. So I had to flip those. So midterm review is next week, Tuesday, and then we'll start the midterm next Thursday. It's open book, open notes, open internet. It won't be due until the next time we meet, which is the 11th. So maybe that works out. It's a little earlier than I thought, but take all break. You can even do it on the 11th if you really want to. I don't particularly care when you take it. And I'm sorry I missed you last week. It was not my best week. Not my best week at all. So we're gonna move. I think we don't need to get to trees yet, so I'm going to move trees to priority queues. We'll see how far we get in this one. So this is chapters 8 and 9 here, and then we'll just do linked lists this week. And we'll just leave a blank here, I guess, right? So it's catch-up time. I don't know. And then all the dates were wrong, which I know the dates repeat from February to March. So I don't know what I did there. But I had Monday, Wednesdays instead of Tuesday, Thursdays because my dates were all off by one. I think all the way through April as well. So I think that's better now through April. I think I got all those right. Yeah, April 1st, April 8th, and the 15th. So the 17th is the last time here. All right, so I'll put that new one back out here. And come on. I'll replace that. Oh, I gotta close it first. Sorry. Retry. Okay, so got that updated. And then I finally did remember to post quizzes now that someone asked about the midterm. So there's quizzes out here. They're untimed, open book, open notes. They're pretty basic. So if we take a look at like the stacks and queues one, I gotta preview it here. Hang on. Updated it to this new quiz format, which is weird. So 3 ways of interacting with a stack. What are the public functions of a stack? How about a queue? Uh, why does a circular queue give you better memory usage? So they're not like just true false questions, but they're pretty short answers here. Like, was this circular queue better in terms of memory usage? Um, and then what's the advantage of using one if we're solving a problem? And then what are the average times for these for all of our major operations? And this is assuming the good queue, not the bad queue, right? We've done a good job with our queue, right? Not the lazy first one here. So just real quick questions for those ones here. That was 6. Um, how do I go back? Go back. Go back. There we go. And it goes all the way back to chapter 2. There is no quiz on chapter 3. That was just the performance analysis chapter, which is rather dull, and we're skipping a lot of it. Um, so this one's like, why in English? What does it do? What does remove do? How does this deliver? So just real short answers. Like I don't even. It's like a sentence. I don't need a paragraph for these, right? But you'll want to have at least looked at these before the midterm because I use these same quiz style questions, so it's the same format of questions. If you don't get them done right away, that's fine. I'm not too particular because I just put them all out here late. Uh, but 2, 4, 5, 6, and 7 will all be fair game for the midterm. Those are all the chapters we'll have covered then by the time we figure out linked lists this week. All right, and then we've got our next project, right? That one is due today. Do we talk? We talked about project 1, right? Do we do the solution? No, we didn't, right? Because I missed you guys. Is that what happened? Okay, so we got to talk about project 1 and then start on project 2. Let's pull this one up here. Project is 2001. Project 1. Okay, so we're doing a recursive backtracking checkers solver here to see what is the most number of jumps, max number of jumps here that we could get given a checkerboard. So we have to go build out a checkerboard here, right? But mainly the get max jumps piece here. So our init for the checker solver takes a 2D board, validates to make sure they're valid, right? So the right size and all the pieces are on the right color here. Then we can figure out for one checker, and then we can do it for all checkers. Right? Doing it for one, that's the hard part. Doing it for all of them is just one extra loop, tracking some values here. A little bit more work, but not too bad here. So we got to write our checkers solver class here. So we can have a class for checkers solver. And our init that takes a board. So we want to check to see if it's valid. So if the length of board is 8 or is not 8, right? And the length of board at 0, right? I guess maybe all of them, but uh, that's probably a little bit trickier to check. I guess we could. We could say and all length of row for row in board uh, equals 8. Or I'm sorry, if they should say what any do not equal 8. So if any of them does not equal 8, right, because this is our check to see if it's invalid, we can raise some sort of value error, invalid board. That's the size, right? So we check here. And this is just a quick list comprehension. If you can do a loop instead, those are fine too, but this will be if any of them is true. So if any of these is not 8, the whole thing's bad here. Then we want to make sure that all the checkers are on the same color. Now, that's a little bit harder to figure out here, but the idea is they're going to alternate. So the first checker that we find, all the other ones have to be on that same color, right? So we can assume whatever the color is that one, right? It doesn't matter if it's white or black. We just need to know that they're alternating. So we need to find out which row and which column it's in, right? So for row in board, and then for what is it? This is column. I guess do we need indexes? We probably need indexes. So for row index in length, the range of the board. Nope, range the length of board. That's backwards. Range the length of board, and then for column index and the range, the length of board. And we know it's already 8 here. I guess we could just do 8, right? Because we're only solving for 8. Because we already checked for size here. Then we're going to need to find the first checker piece, right? So if my board at the row index at the column index does not equal like an empty here, and again we could add in some nice, empty. There's a space here, so it'd be a little bit cleaner. Self.empty, maybe even like a max size, board size. This will be even nicer here, right? Then self.board size. Replace that board size, just to avoid all those magic numbers here. It'll be a little bit nicer this way. I got a little long. All right, so if it's not empty, then I need to know which one it was. Now, it's a little bit awkward when you look at a chessboard here, a checkerboard. Chessboard. We just wanted the blank one, right? Sure, that'll do. So if we were to number these, right? If we were to add it, let me copy this, right? I can do my little clip tool here. Snip tool. New capture. No. So photo. New snip. There we go. Okay. So if we were to number these, right? This is row 0, row 1, row 2, 3, 4, 5, 6, and 7, and then column 0, 1, 2. Wow. I locked up my mouse there. 3, 4, 5, 6, and 7. So if I look at the sum of the row and column at 0, 0, 0, 0, 2, it's 2, 4, 6. So those are all even numbers, right? In the next row, 1 and 1, 2 is even, 1 and 3 is even, 1 and 5 is even, 1 and 7 is even. So you notice they're either evens, right, for white squares, or they're odds for black squares. So that's how I can tell then which one it's supposed to be, right? So I can look at, hey, what is the sum of the row and column index here? is it even or odd? So I've got even squares and I've got odd squares, right? And they follow that number pattern here. So we need to know which one it's supposed to be. So pieces, I don't know, on even. We'll assume it's true to start because we don't know any better here. Okay. Whatever we find then is going to be true or false. So we can say, okay, if it's not empty, then it must be a checker, black or white here. Then I can check to see. So my pieces uneven then will equal my row index plus the column index mod 2. Yes, sure, equals 0. Right. So if there's no remainder, then they're even. If this is false, then the whole thing is false anyway. Right. So I found the first piece. Right. So I know it's got to be uneven. Right. Actually, I guess I should set this. This should be none to start. Right. There we go. So if piece is uneven is none, then we'll go set it here to that value. If it's not none, then I have a value. I know it's true or false. And then I can see if this new spot here then, so if my piece is uneven, so this will be true or false, right? So this one, if that equals the row mod 2 equals 0, right? Where all of this one then is now going to be true or false. So if they were uneven and I add them up and there's no remainder, it's even again. Life is good. But if they're not, then, right? So if it's not matching here, then I can raise a value error. Pieces on more than one color. Okay, all of this just to validate the board here. But we're going to go and check. Right? So if we found if they're even or not, then we'll go and see. Hey, if they don't match here, then we can stop. Okay. If we've done all of that, then we validated. Great. Now we have a self board equals the board. Right, we're good to go. Okay. Then we can just go copy it. We had a print board here for one of these. 2001. We did is it the lab exercise, right? Where we did the queens. Did we do that one? Yeah, I printed this one here, right? So we just joined the board together. We'll just steal this one here. So there's our string function. And look, if I copy pasted it, I might as well go cite my source here. Let's be good, right? Come on. Right. Okay, so we can print ourselves now. So we can print out the board here. And it'll just be the spaces on it. It's not going to be the prettiest looking board. We won't have like grid pattern or anything, but that's okay. If we wanted to make it cleaner, we could. But this is fine for now. It'll get us something. All right. So we've got the board. We've got it checking to see if it's valid or not, right? So we got black for black pieces, W for W pieces, white pieces here, and then our get max jumps, right? So we'll have a get max jumps next. So define get max jumps. Okay. Now, this one checks for one checker here. So maybe we tell it which checker, right? Maybe you tell it the row and column, row index, index and column index. Right, so we can do it for one checker maybe. Right, so hey, if there's a checker here, let's go and see how far it can jump. Right, if you don't have this in here, then it gets a little harder to find. You could do it for the first white checker, or we just kind of loop it together. We do it for all of them. Both ways will work. All right. So for a single checker, then essentially what we were doing in English, right? We had, can you go this way? Okay, go ahead and do it. Recurse. Can you go this way? Go ahead, do it in recurse. Can you go this way? Go ahead and do it in recurse. Can you go this way? Go ahead and do it in recurse. Right? So we've got this like list of moves then, right? If, like really, probably a tuple's fine, and each one of those then is going to have another direction. So up and left, right, was minus 2 rows, minus 2 columns, right? To go up and left. So we can have minus 2, minus 2 for the first one. And then to go up and right is minus 2 rows, but plus 2 columns, right? So minus 2, plus 2. We did something similar with the Knight's Tuber, right? Where we had this list of possible moves the Knight's Tuber could do. I think was the easy route for that. And then we have going down rows, but back columns, and then we have going plus rows and columns. Right, so these are all the different possible directions we can go, right? Then we need to see if we can do it, go do it, right? Because we're going to recurse on this here. So we also need a way to track the number of jumps that we have, right? Why is it cranky about this? Oh, because we haven't used self yet. That's fine. Yep. So we'll have a define can jump to, and we need a row index. How about a current row index or the start row index, a start column index, and a target row index, and a target column index. So tell me where you are, tell me where you're going, right? And I'll tell you if you can jump to that spot here, right? Okay. So for every one of these, we're going to see if we can, right? So for move in moves, if self dot can jump to. Now, my start row index is my row index. My start column index is my column index. My target then is going to be my row index plus move of 0, right? Whatever that first move was going to be, change my row here. And then my target column index will be my column index plus move of 1. I grab the next one here, like we do with the nice tour. So if we can do that, then we go and do it, right? We don't know what we're doing yet. We don't know how to figure that out, but we will in a minute. So if we're going to go do it, right, we need to be counting our jump, right? So we need a way to count our number of jumps. So maybe we have a self dot current jumps, right? So we can track current jumps. So if we can jump, then I'll take my self dot current jumps, add 1 to it. Then I'll take my self dot board at the row index, at the column index. I'll set that to self dot blank. Do I not have a blank? I don't have a blank. Oh, empty. That's right. Right. Move my piece. So move where I was, make that spot empty, right? Then self dot board at the row index of move, at the column index plus move. That one here, right? There we go. 2 dimensions here. Board, there we go, is going to be self dot. What's the probably the white piece, right? I think we're only assuming white piece, but we could make it work for either here, right? So I guess before we move that, then right, put this one down. We'll equal whatever was here, right? Oops, that was 2 copy paste. So put what was there, then mark it as empty. Why is it not? I'm missing another parenthesis. This one here too, or square brace. There you go, square brace. All right. So where we're going to go, our destination, set it to where it's currently there, and then blank out what's currently there. Right? So that's our move. We're changing the board. We can jump, so let's go jump, and then we're going to recurse. So self dot get max jumps. And this should return something, right? So we're going to return self dot max jumps. Well, we don't want to return actually yet because we need to be tracking that. So eventually we'll return a value here, but we'll get there. So get max jumps. Then we're going to recurse on that function. And then the new location, right? I guess we should just save this here then, right? So this is new target row index. I feel bad doing this like 5 times here. So we should target column index. Here we go. And we can use these instead everywhere. That'll make life a little bit easier here. And then our target column index, our target column index, and our target column index. Right. Okay. I think I've replaced all those. So just to make that a little bit cleaner. Excuse me. So if we can jump, count the jump, I'll move my piece, take off my piece off. Oh, but we're missing the middle step, right? We have to also remove the piece that we took off the board, right? When we jump over a black checker, you have to take the black checker off, right? So self.board at the current row index. Oh, goodness, here. Row index plus the move of 0 divided by 2, and we need that to be floor division, so we always get an integer value here for that arithmetic to work, right? So if move was -2, I want -1. If it was +2, I want 1, right? But I don't know if I should add or subtract, right? So just floor divided by 2 ought to do that here. And the same thing with this one, my column index plus move of 1, floor divided by 2. Then that one also becomes empty, right? Because we took the piece off. But you jumped over it, remove it. So now I've got 2 empty spaces here, and wherever I landed here. Now, if we wanted to keep track of this here, this was the jumped piece, right? Jumped piece could equal what was here. It'll make life a little bit easier for us. So when we come back from our recursion here, right, whenever this is finished, whether or not we have more jumps or we don't have more jumps, we need to undo that step so we can try the next jump in our possible move and moves, right? So we're undoing here. So we're taking all these steps here and undoing them. So actually, let's go backwards here. So the row index, column index, instead of being empty, it needs to be my piece. So I guess I guess we should save that then. Piece is this one here. So put it back to the piece, right? Then put this one back to the jumped piece, right? The piece that we jumped over, we removed, right? Then undo this one. Let's see. Trying to go in order here. That one was empty. That was the piece. That one here. This one here. The target column index here now becomes empty. Right before we put it to the piece we were jumping here, it should be this piece here. There we go. We should move these. Let's make this a little easier. So here's the jumped piece. No, regular piece here. Right? So we undid this one here, with being empty. We put our piece back. We undid the jump piece that we jumped here. We undid our target here. And then we're going to uncount that jump, self.current number of jumps, -1. Right? So we change something, we recurse, and then we undo it so we can keep on going from here. Right? So eventually we'll have tried every single move here. Why is it not like this now? Function. Oh, I never finished this one out here, so I can jump to. Okay. So this should hopefully work then, right? We haven't figured out how to track the max number of jumps yet, but we can get there, right? So our max number of jumps then, right? We can say, hey, here's our max jumps is 0, right? And then every time we jump in here then, right? That should be a self dot value here. Let's have self dot max jumps. There we go. 0 self max jumps. So we don't want to change it to 0 every time we call get max jumps. We want to do it, check to see if we're going further. Right, so every time we do jump, then we can take self.max jumps equals the max of self.current jumps and self.max jumps. Right? Whichever one's bigger, take the bigger. If you have no current jumps, sure, we stay at 0. If you have a current jump, right, now let's see if it's bigger. We're going to take the max here to see the max number of jumps. When all of this is done, then we can return self.max number of jumps. Right? So the can jump to, then we need to see, can we jump over a piece? Right? So this is, we're going to check to see if our target is valid, right? Because you can't jump off the board, right? If it's a valid target, then is there an empty space for you to jump to? And is there an opponent in between you, right? So first we can check if the target row index, we should go, 0 is less than or equal to the target row index is less than self.max size, board size, right? So if that's valid, right? And my 0 is less than or equal to my target column index is less than self.board size, right? Then that's good, right? Okay, and then we'll have and So if you're within the board, then we're checking to see if it's empty. So self.board at the target row index at the target column index is self.empty, right? We're blank. We're within board, we're within bounds, and we're blank. And then the halfway point, right, is an enemy piece to jump over. So can't be empty, but it has to be the opposite team, right? So it's easier if we just check for black. It'd be nicer if we said, hey, if this one's white, is that one black? Or if this one's black, is that one white? Can we just be cheap and just check for black piece there in the middle? Is that okay? All right, no one's too upset by that. So to figure out what's in between them here, right, that should be the average of them, right? If I add my row and my target row and divide by 2, is that going to match? So if I'm going from 4, 4 to 6, 6, right? If I add them up, the middle should be 5, right? So here's, I don't know, we need like the midpoint. We can just do it here. So and self.board. This is going to be a little bit ugly, but that's okay. So we're going to take the midpoint. So we're going to take the start row index plus the target row index, floor divided by 2. Right, that should be the midpoint, but then we want to force the order of operations here. Right, make sure we do that addition first. Right, then at the same at the column index, we start column index plus the target column index in parentheses, force that order of operations, floor divided by 2. If that equals, we'll just say a black piece for now, right? Again, we should clean that up here. This is black. So B, white is a W. Let's see, so is self.black, right? So if we're within bounds and there's an empty spot and there's an opponent to jump over, we're in pretty good shape. Okay, so if that's all true, we just return that as true. If any of it's false, the whole thing's false, right? So I think we just need our backslashes here. Make Python happy. Tracking okay so far? So really, we could put that in here if the can jump, but that looks a little ugly, right? Um, if it's just one statement. I don't know if we've saved a whole lot, but I think it makes it maybe a little bit cleaner here. Now, this is sure a little bit ugly. We could move this into its own function as well, like a do jump or something. I don't know. We've got options here. It doesn't have to be one big function here, or like do jump and undo jump if you wanted. Sure, we got lots of choices. However you want to try and clean that up here is okay. But ideally, that should give us the max number of jumps, so we can try it. So we'll have a board. Here's our 2D board. So we need 1, 2, 3. Oops. 4, 5, 6, 7, 8. Oh, we have one of these from the End Queens. Oh no, I don't think I did I? That's right. So there's one of those. 2, 3, 4, 5, 6, 7, 8. You don't need that last comma. Right? So what do we want to do? So we can set up a little scenario, right? I think we did one where we had, was it like, there was a white checker here and a black checker here. So we would land, I gotta be one over more. One more. So a white checker here, black checker here. So we could land here, jump this one, land here, jump this one, land here, jump this one, right? And then over here, we should be able to land over this way if we wanted. So multiple paths we can take, right, for jumping. We can just jump once and be done, or we can jump once, twice, 3, 3, 4, and then 5, right? We should be able to do 5 jumps that way, right? If we successfully remove this one here, right? We can give them some other checkers this way here if we wanted, like a black one here, and then we should not be able to jump over one this direction. Right? Make sure you don't jump off the grid. Any sort of testing we wanted to check in here should be good, or put like another checker over this way, maybe, right? So maybe you get 1, 2, or 1, 2, 3, 4, 5 that way, right? Or 1, 2, 3, 4, 5 that way. 5 we land here. Yeah. So I think 5 should be the max number of jumps. So there's a couple different ways we can get to 5, but that's okay. We'll check, right? So this is 0, 1, 2, 3, 0, 1, 2, 3, 4. So from 3, 4. Okay, so we'll make a checker solver. Solver is a checker solver given the board, right? And then we'll call solver dot get max jumps given 3, 4, right? Row 3, column 4. And that should return something, right? So we can be able to print whatever we get from that. And we get back 5. Seems to work well. We could print the board every step of the way if we wanted to watch it do this, which might be fun too. Uh, right? But what if we put another white piece in here? Right? Can we throw another white piece somewhere? We have a white piece. We must be able to do some other jumps, right? If we threw it over here, this one could get 1, 2, 1, 1. This one can get 1, 2, 3. Right? So with a second piece here now, it should be max of 3, right? So then to get max jumps, if we don't know the row and column index, right? Well, we want to do it for every white checker. So we know the board's valid, so let's go through and find the max jumps for every white checker here. Um, so we can have another define get max jumps, and then for row index, is it gonna let me? It's not gonna let me do it. Shoot. Oh, maybe it will. Max jumps index. Where's my little loop here? We have one of these, right? Row index, column index. If my self.board at the row index at the column index equals a white checker, then we'll call get max jumps, right? So we need a max jumps here equals 0 to start. Oh, I guess it's gonna set self max jumps anyway, won't it? So that's fine. So we'll call self dot get max jumps given the row index and the column index for every white piece that we find. Dot usage. Are we doing this bad? We're doing it bad, aren't we? It's not gonna work. Get max jumps. Yeah, shoot. Okay. Get max jumps. So we need to do this one instead of this one here. That's fine. So we'll just call this a helper function. We'll make this one a private helper function. We recurse, make sure we call that one here, right? There we go. And then this one then should return self.max jumps. Right? Now we get 3. That's what we expected. So now it's going to try every white checker and see if we get more moves. Right? Maybe we'll move that one here. We'll put it over here. Right? So it's got 1, 2, 3, 4, 5. It could also do. Right? That's got some fun moves that direction then, right? 1, 2, 3. Yeah, I think 5 is going to be the max then. Right? If we put it in the middle. But both of them can do 5. But that's fine, right? So the most number of jumps we can get is 5. So we did it for one checker, and we did it for all the checkers. That make sense? So maybe we didn't need the stop in the way to just do one checker, but now we've got a nice little loop that we can use for doing one that we just do for all. Right? You okay so far? All right, awesome. And put that out in GitHub before I forget. Project 1. All right. I started getting through some of the projects, and I'm behind on that. A couple people didn't have unit tests. I was confused on that for Project 0, but we'll get there. All right. New stuff now. Right, moving on. 2001, this is week 7. Linked lists. Right, I think that's what we're covering now. Just updated the syllabus. I should remember that, right? You guys should remember. We just updated it. Yeah, linked lists. Okay. So chapter 7 linked lists. So all this time we've looked at these array-based sequences. We're finally going to do something different than array-based sequences here. Okay. Now it gets to be really interesting. Now, this is a little bit of an awkward data structure to start with here. It's a little bit awkward. Um, and it's not going to seem very useful at first, but as we look at what it's fast at, it's going to be faster at insertions than array-based lists. Like our array-based lists, if you want to insert something at a specific index, how long is that going to take based on our n number of items? Oh, then, yeah, the more things you have, the more things you have to shift. So linked list says, I can do it in constant time here. I can put something in the middle of a list like that. The problem is you have to know where that middle is, and we'll look at what that is here. You can also remove things like that. With our array-based list, you had to shift n things over, so there's no shifting with linked lists, which is really powerful. So we're going to write our class for, we're going to start with a singly linked list here to start. So singly doesn't mean a whole lot of stuff yet, but that's okay. So a quick way of visualizing this is thinking about, you know who comes after you in line. Right? Imagine you all get in a line and you know who's behind you. And someone says, oh, I have to run to the bathroom real quick. Can you hold my spot? Right? So they run off. They're not actually behind you anymore, but you know they belong there. Right? So you know who comes after you. So you're referencing who comes after you. And when they come back, you're like, oh yeah, come back right in line here. You were behind me. And they fit right back in. It's pretty easy here. So with a linked list, we have these links where you say, I know what comes after me. I know what comes after me. I know what comes after me. So they usually actually do this with an inner class, which is really weird looking here, but that's okay. So we're going to have an inner class that's private to singly linked lists. So when you use a singly linked list, you don't have to know anything about this node here, but we're going to use these nodes everywhere. So nodes have the data that we're storing, and they have a next. And we're going to assume that's none until you tell me otherwise. So self.data is the data, and self.next is the next. Now, we don't even need to try and make these things private. This is just a private helper class, inner class here as we're going. Right? I'm not going to put underscores and have get functions and set functions. It's just a way to store those two pieces of information here. Okay, so when you create a singly linked list, then I'm going to have a start, or they usually call it head here. The head node or the start node here is starting off as none because I don't have anything now. I'm empty, right? But then I'll also have a self dot number of items, number of items here. Oops, I should set that to 0, right? So we have no items to start, and we're empty. So we can have a length here. You return self dot number of items. Then we have a is empty. I think we use that one here with our stack and queue. So return length of self equals 0 here. Right. So now if you want to add something to the list here, we can add. So we'll define an add, and we want some piece of data here. Right. So you're going to add some piece of data to our singly linked list here. So you can say, hey, if self dot head is none, then self dot head equal the node given the data. Right. Self dot node. Yeah, there we go. So make a new node. Here's your piece of data. There's nothing next. If it's not none, then my self.head will equal self.node, given that piece of data, and what was formerly the head item here. Right? So I'm going to say, okay, you're the new front. You're the new head. There's something that comes after you. All right, you're the new head. There's something that comes after you. You're the new head. There's something that comes after you. So in terms of performance for this one here, no matter how many n items I have, how long is this going to take? One, it's constant. And on the worst case performance, it's still O of 1. It never has to resize. There's never an array that we say, oh, you need to go get twice as big, and I have to shift, copy, n things over. I'm always just adding to the head. Oh, I'm just adding, I'm just adding, I'm just adding. Now, this is a little bit obnoxious here if you don't want things to be in reverse order. Right? It'd be nicer if it was append rather than add, and we can fix that. So we can have append. But to do that now, we need to track a is it tail, I think? Say, hey, there's now a back, or a front and back. Oh, head and tail. Do you like front and back better? I like front and back. That's probably easier. We'll say front and back here. Okay. So to go add something, this is my front is none, and my back. Oh, that's still front. Make a new node. So here's my front. Now, but I don't want to add these things to my front here, right? So if the front is none, if I don't have a front, then I have a new front, and I also have a new back, right? Is self.front, right? So if I was empty, now both the front and back are the same node. Now to add things or to append things, I just need to add them to the back, right? Now this gets a little weirder looking though, because I know where the back is, right? So my self.back, oops, self.back, this is the last item then. I don't actually want to make another back, right? I can't change it yet, but I can say, hey, your next then equals a self.node given that data, right? Remember this little node here? So sometimes it's nice to draw this in a picture here. Let's draw a little picture. I should have brought my tablet. It's always fun. So a little node here, right, has some data. We'll put D for data. And then a lot of times you put a slash for none for your next here. This is next, right? And here's our data. Okay, so to add something new, we say, hey, you're next now. You're not none. You now have something that comes after you, right? And you draw a little arrow and say, hey, you point to this one here. Here's some piece of data here, and that one doesn't have a next. Right? I've just added to the end. I've appended here. Right? And just keep on going. The last thing I have to do though is I need to change back though. Right? Now self.back now is going to point to self.back.next. Right? If I added something that comes after the back node, this direction, right? Then I have a new back. I have a new tail, footer, whatever you want to call it here. That's the new back of my list here. But I'm still O of 1. Right? Still get constant time performance. No matter how many n items I have, it's constant time to append. And worst case, it is always constant time to append. So I never have the resizing. This thing is always fast. Right? Now what we've done is we've traded a little bit here with some memory usage, because node now has to store another piece of information here. So I'm storing the data, which we always have to store the data, but now I'm also, for every piece of data, storing the next memory reference to the next node. Not quite, it's probably close to doubling your memory usage, right? So if I've got a million things, now I have a million memory references to the next thing and the next thing and the next thing and the next thing and the next thing. Not a ton here, but there's a small trade-off. So we're gaining some speed at the trade-off of using a little bit more memory, right? Because we're storing a little bit of extra data here. Now, to remove the last thing is actually really hard to do now, because I know where the last thing is. But if I go to remove that, I don't know what comes before that last thing. Right? I only know where the front is and I don't know where the back is. So removing from front is really easy. Right? So we can say, hey, I want to remove the front. Remove front, or like DQ, right? If we wanted to DQ something, right? If we imagine this as a queue, I can say, here's my, I don't know, my data is self.front.data. And then to remove this one from the list here, all I need to do is say, hey, let's change what the front node is here. Your front now then is equal to self.front's next. Right? Just change where the front is. Okay, you're no longer the front. The thing that was after you is the front. Now, this only works if we're not empty. So like we could say if self.is empty, raise a value error or something, error empty. I don't know why I keep doing that. Yeah. So if we're empty, you can't do it. But if we're not empty, great. Right? Now, this should be fine. Right? We just keep going to the next, going to the next, going to the next. But now we need to also take our self.number of items -1, and then we can return that data. So we probably also want to add something, right? Take our self.number of items +1. That'd be useful, right? To make sure we have some items here. We can remove from the front. We can append, right? We could see what that front value was without removing it, right? Or like a peek, like we did with like stacks or queues, right? Tell me what was the front item here. But right now, we essentially have a queue built out of a singly linked list here with worst case performance of O of 1. No matter how many n items you have, you're never going to have to resize. Never going to be slow. So now we have a more efficient way of storing all this data, and that whole circular queue that we wrote can just go away and just be a linked list queue. Right? A queue built with a singly linked list. We don't need to manage, hey, I have to move things over and I have to wrap around, I have to take things out. Sure, you've got the front, you got the back. Right? You can add to the back, take from the front. Easy. These are fast. Now, things that are still slow, though, right? Trying to find some particular item. So if you wanted to have find some piece of data here, well, to see if I have this piece of data, I have to go look at every single node, right? So for node, so you want to say while, so the current node then is going to equal self.front. Okay, so start with this current node, and then while my current node does not equal none here, let's keep on going. So if I'm not a none, let's go. So if my current node dot data is equal to the data, I return true. Okay, if it's not, go to the next one. So it's current node then equals current node dot next. Go to the next one. Go to the next. Go to the next one. Go to the next one. Go to the next one. Oops, that should be is not none. That's why I was complaining here. So as long as we're not none, is not none, right? Starting at the front. If we're not none, go check. If we're not none, go to the next one. Go to the next one. Go to the next one. So we're saying, okay, start with this one here, and then go to your next one. Go to the next one. Go to the next one. Go to the next one. So as we add nodes, the operating system gives us a little bit of space in memory for this new object. We say, hey, I want to put a new node somewhere. The operating system says, sure, put it over here. And then we just point over here. And we want to add another node. Operating system says, sure, have some memory over here. Great, now point over here. A new node, new node. So they're not a contiguous block of memory here. So we can find something, right? So this one then is going to take, we have to go look at n things, right? So it's an O of n operation. And if we haven't found a true, then we can return false by the time we're done. When this loop is done, when we got to none, we didn't find it. So find is always going to be slow with this one here. Did we do finds with our arrays? I don't know if we did or not. Those ones are still slow, right? Because you just have to go look at everything. Now, what we can't do easily is go get something by index. Right? Do we do the indexes? I really should remember this now, but I don't because it's been like a week with our array-based lists. This one here. Append, remove, find. Yeah, get item here. So, oh goodness, that was fast. Yeah, we did a find. We did. Right, so get item here. Right? Goes and gets it really quickly. That was constant time. If we wanted to have a get item at a given index here, so we can define a get item by an index, right? Get item at a given index. Yep, for a given index. Now, I don't have an array that says, hey, go to this index. This doesn't work, right? But we can check. We can say if index is less than self.number of items, or I guess we check the other one, right? So if index is less than 0 or index is greater than or equal to self.number of items, we'll raise an index error. I don't think we need anything other than that, right? There's no message that just is an index error. I think that's fine. But if it is valid, then when we can do this, we just have to count ourselves, right? So we can say current index equals 0, and then also we need then a current node equals self.front. And while current index does not equal the index, right? We can keep on going. I'm going to say, as long as I haven't got there yet, my current node will equal the current node's next. Go to the next one. And then take current index plus 1. Go to the next, go to the next, go to the next, go to the next, go to the next. Hey, you want index 20? Sure. 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 20. When we're done, we can return current nodes.data. Now, how fast is this one, though? That's O of n, right? Or k for index, right? We got n. Right? The bigger n things I have, the more it's going to take, right? Because I have to go count and walk those many nodes to get there. I don't have a fast way of going about it here. which is a bummer. So it's slow at getting things by index, but it's really fast at adding and removing from the front to back here, right, with our singly linked list. That part makes sense? Now, the other thing we haven't done yet is when we remove the last one here. So when we removed front, we became the fronts next, but then we might have had back be broken because this works if you have one item. Front is now none. Now we need to check. So if my self.front is none, then self.back has to be none as well, right? If you took the last item off, then you no longer have a back, right? Because we use back for some of these things here. Not a whole lot of things actually, but we don't want to be hanging on to referencing this location here. Won't get garbage collected if we're not careful. So make sure that we clear out back so that it will properly set back to what it needs to be here as we go. Okay, so get item, check for valid index, set item. We could set items too. It works the same way if you wanted. So let's go do that one, right? Define set item, given the item, the data and the index here. Is that the right order? I don't remember. Index first. And then I guess we'll call it item, right? Why not? Okay. Oh, that's underscores, double underscores. There we go. That's why I didn't suggest it for me here. So we have to do the same thing here, right? Keep on walking here. And then eventually we'll take our current nodes.data and assign it to the item. Right? Whenever I got to where I need to go, we'll go change it. Yeah. Oh, yeah. Thank you. That's why it turned purple. Yep, perfect. Now it has that here. So just go find that item. You have to go walk to it here, but then we can go set it really quickly here. But it takes a while to get to, right? So this is still O of n, right? The more n I have, the longer it's going to take given my index here. So it's slow at getting and setting, right? So it's just a trade-off. So we're saying this one is faster at these certain things and slower at other certain things. All right. There's more to it, and we'll do more fun things here with other links here. Um, and we can add uh, these are singly. So the next one we'll do is a doubly linked list where we'll know what goes before me and what goes after me. We'll know both directions with double links. We can do that one on Thursday because we got to talk about the next project. I don't want to get too far behind on this one here, right? So we're going to do a stacks and queues and next project next, right? So we go shamelessly copy paste here. If you give me just a moment. We'll go add a new assignment for project 2. Now this one is not as bad here. So this is stacks and queues. And then we want 2 weeks for this one, but we had break over the 4th, so it'll be to the 11th, the start of class here. Same time the midterms do, but I promise it's not too bad, right? Shouldn't be too bad. I think this one was, I gotta look how many points it was here. This one. Nice stacks and queues. So that's linked objects. Shoot. Did I do it wrong? Stacks and queues. There we go. Aha. This looks like a bunch of nonsense. Don't worry. I promise it's not. I mean, it is a little bit, but that's okay. Let's do 20 points for this one here. All right, and then save this one and add the rubric. This is project 2. So you get 5 points for use of object-oriented programming. You've got classes with private attributes, public functions, right? And then our trains calculation is correct. And then we'll get to that in a second. We'll get the planes calculation is correct. And then the last one here then is trains uses stacks and planes uses queues. So actually using stacks and queues specifically here, not a Python list, right? Stacks and queues. not the list here for that one here. We'll use that for grading. All right. Sounds really long, but it's just a bit of a story here. So remember, stacks and queues work if they fit the problem. And lo and behold, we have a problem that fits stacks and queues. Who knew? I'm sure you're all very surprised. So what we're doing here is we're imagining a piece of software that will calculate how long it takes to load planes and trains from a given cargo ship. So cargo ship comes into the dock. How long does it take to unload all these containers that go to trains and all these containers that go to planes? Right? We haven't even optimized anything yet, but I just want to know how long it's going to take. So for us to do that here, we're going to start unloading things from ships here. So we're going to assume that everything gets stacked up to 5 high. These big old containers here, you take them off, you're going to make stacks of 5. If you go higher than 5, OSHA is going to yell at you as long as they still exist here, hopefully protecting people for a while. Uh, no higher than 5. So grab a container. If it's for a train, put it down. Grab another container. If it's a train, put it on top. Put it on top. Put it on top. So we get to a 5 high stack, and then you start the next stack behind it. Right? So we've got a queue of stacks. Right? I put them closest to my trains, and then next closest to the trains, next closest to the trains, next closest to the trains, next closest to the trains. Here with that? And each of those items is labeled with the train number or plane number. Hey, these go on train number 1, these go on train number 2, these go on train number 3, these go on plane number 5, whatever happens to be here. Right, new stack. So for planes, imagine we've got some big long conveyor belts heading out to the airport. I don't know, that's fine. Big assembly line. There's one line here. So plane items just get queued, right, into a line. Train items get queued in a stack, right, a queue of stacks. Stack 5, stack 5, stack 5. There might be 2 left, stack 2, whatever's left here. Okay. Now, we've got 2 people working. I don't know why the dock union only lets us have 2 people working. That's fine. That's up to them. So one person loads trains, one person loads planes. They're both working at the same time, right? So independently of each other here. So to load a train here or a plane, the smaller number ones are closer. So train number 1 is closest to my dock. Train number 2 is further. Train number 3 is further. Same with the planes, further and further and further. So it takes 2 minutes times the train number to take an item. Hey, this item on the top of the stack in front goes to train number 3. It takes 6 minutes to get there and back, right? Because it was train number 3. Then I'll grab the next thing on top of the stack in the front of the queue of stacks. Hey, this goes to train number 1. It takes them 2 minutes to get there and back, right? On and on and on. When that stack's empty, assume the next one moves up, right? Take that one off the queue, have your next set of stacks there, and you load all the train items. For planes, the airport's a little bit bigger here. It takes 10 minutes times the plane number to get there and back. Hey, the item in front here of this big old conveyor belt, whatever happens to be, my line, goes to plane number 3. That's 30 minutes to get there and back. Train number 4, 40 minutes to get there and back, whatever it happens to be. So we have to figure out the total time it takes to load all of the trains and all of the planes. Okay, so for input, this looks really silly. I've copied this project off of Dr. Ellen Bogan, who used to be here. He ran the competitive programming team competition. He helped out with that. They're big on this sort of nonsense input. Sure, it's okay. It's fun to have one practice here where you've got some really specifically defined input and output here, and there's either right or wrong. There's no middle ground here. So for inputs, 4 lines here. The first line has 4 integers, T, P, NT, and NP. Trains, planes, number of items for trains, number of items for planes. So how many trains, how many planes, how many items for trains, and how many items for planes for my first line here. We've got 0 to 100 trains and 0 to 10 planes, and 0 to something and 0 to something. So as many items as we have items, right? There's real no limit here. They're just space separated. Okay. The second line then has key integers here. So this is the number of items loaded into each train. I'm sorry, it's 5 lines of input here. So sometimes it's easier to look at the input here. So 3 trains, 2 planes, 10 items for trains, 5 items for planes. Okay, that's our first line. The next one says train number 1 gets 2 things. Train number 2 gets 7 things. Train number 3 gets 1 thing. The next line is the number of items for each plane. Plane number 1 gets 3 things. Plane number 2 gets 2 things. Okay. Then the next line is for each of the train items, which train does that item go to? And this is the order in which they're pulled off of the cargo ship. So of the 10 items on the cargo ship for trains, first one goes to 2, the next one goes to 2, the next one goes to 2, then 1, then 3, then 2, then 2, then 2, then 1, then 2. So what train number is this container going to? And then what plane number is this container going to? And then what we spit out is the number of minutes it takes until each train is fully loaded, and the number of minutes it takes until each plane is fully loaded. So again, we can draw this one out here. This is easiest if we draw it. Let me go copy this input here. Okay, and then we'll draw it. So when we're unloading items from the dock here, let's put it a little bit here. There we go. Right, I have train 1, train 2, train 3, and I have plane 1 and plane 2. Okay, I have this big long queue of stacks. This is my queue of stacks here for my train items. So the first item that comes off the cargo ship goes to the queue here, right? Train number 2. Got that one. The next one gets stacked on top. Train number 2. Great. Stacked on top. Train number 2. Stacked on top. Train number 1. Stacked on top. Train number 3. Stacked on top. Train number 2. Well, I'm 5 high. Can't put any more on. OSHA will get me. Right? So start the next stack in the queue. Right? Train 2. Train 2. Train 2. Train 1. Train 2. Right? That's my queue of stacks. Right? And then just my regular queue for the plane items, I have 2, 1, 1, 2, 1. Right? Imagine this is the front here, if that makes it any easier for you. Right? These things. Okay? So whatever numbers we have here, we just load up. Okay? The loading part, the unloading part, we don't care about. That's someone else's job. Right? We care about the loading trains and planes job. That's our job. That's what our union takes care of here. For my one train worker and my one plane worker, I guess we only have one high-low or something. I don't know why they won't buy more, but that's politics. So how long does it take to get the train fully loaded? Well, train number 3 gets 1 item until it's fully loaded, right? Train number 2 gets 7 items till it's fully loaded. Train number 1 gets 2 items until it's fully loaded, right? And then 3 and 2 for the planes. You see where the numbers are coming from, right? So as our poor little dock worker here comes over, I don't know how to draw a high-low, so just imagine he's picking these up by hand here. Comes up to the front of the queue, goes to the stack. What's on top of the stack here? Well, an item for train number 3, right? And right now it's been 0 minutes to start, right? So here's my clock. Right, been 0 minutes. That's a clock here, right? Not an orange or something. Okay. So he goes and grabs this one here. It's going to take 2 times to get there and back. So how long do you think it takes to get there? Yeah. Well, that's the there and back. So how long does it take to get to the train? Probably about 3 minutes, right? Yeah. So by the time I take this number 3 here and I go put it on the train here, it's been 3 minutes, right? This item's done. Train 3 is fully loaded, right? The output here says in 3 minutes, train 3 is fully loaded. It has this item, it can take off, right? It can leave the station, okay? Then we come back, and now it's been 6 minutes, right? Because that's the round trip time. I go to the next thing in the stack here. Okay, well, that's train number 1, right? Go add that one here. Well, that one took 7 minutes. I come back, and now it's been 8 minutes. Here's train number 2. I take that one here. It's been 10 minutes. I come back. It's been 12 minutes. Grab this one. Move it here. It's been 14 minutes. Come back. It's been 16 minutes. Take this one. It's been 18 minutes. Come back. That one's unloaded. It's been 20 minutes. Take this one here. It's been 22 minutes to get there. Come back. 24 minutes till I came back here, right? I take this item for number 1. Go load it up. It's been 25 minutes to load up train number 1. It has 2 items. It's fully loaded. Come back, it's been 26 minutes. Here's another item, 28 minutes, 28, come back and it's 30, get here and it's 32, come back and it's 34, take this one, it's been 36 minutes. I come back, it's been 38 minutes total, They only care when the train was loaded, right? I don't even know how many total minutes it was. So you can see how our output was 25 minutes, 36 minutes, 3 minutes, right? 25, 36, and 3. Because we grabbed the item off the top of the stack, took it. Top of the stack, took it. Okay? Planes is much simpler here. This is 10 times the number to get there and back. So to get there is just 5 minutes, right? So plane number 2 takes me 5 minutes to get there, 5 minutes to get back. It's been 10 minutes, right? 5 minutes to get there. It's been 15 minutes. 20 minutes to get back. 25 minutes to get there. 30 minutes to get back. I did it wrong for this one here. 10 times. No, that should have been 10. Shoot, I have the wrong numbers here. Sorry. Let's redo those numbers here. So 10 times for there and back, half of that 5 times for a single trip. So with plane two, it's 10 minutes to get there, 10 minutes to get back, and it's been 20 minutes, 25 minutes, 30 minutes, 35 minutes, 40 minutes, 50 minutes, come back and it's been 60 minutes, get there, it's been 65 minutes. I come back at 70 minutes, nobody cares here. It's not like they're going to pay me for that time, right? And then I have 65 minutes and 50 minutes. 65 and 50, right? It's a bit of things happening here, but we just got to work through it piece by piece by piece by piece. So points for making classes. You want classes to represent things, right? Think about it as an object-oriented manner here, right? How do we represent these things as classes? What data are we grouping together here, right? I think in my solution I have like 3 classes. I'm trying to remember. I forget exactly how. Like however you want to manage it here, right? And then being correct for trains, being correct for planes, and then using stacks and queues. So if you use Python lists, you don't get the points here, right? Use the stacks and queues, right? Okay, copy paste from lecture. I don't care. Write your own, however you want to do it. Go use the book ones. That's fine too. Just tell me where you got them. I don't expect you to write them by hand, right? We've gone over them. The book has their examples, but not using Python lists. Okay? Right. Thoughts, questions, concerns? So we've got 2 weeks plus break. We'll pretend break doesn't exist. We do 3 Tuesdays from now. Look at that. We're already looking to March. Mid-March ought to be somewhat warm by now then, right? Maybe not snow. I don't know. All right. If you got any questions, let me know. If not, I will see you folks Thursday.